Yeah, I mean, I mean, to be honest, next week I don't know what's gonna happen. It's like the week before like the final. Usually there'll be fewer people in class. They'll be trying to like wrap up their projects from other classes. I kind of flat out. Next week will be review session. So if you, yeah, usually there's not a lot of people on the last day of class. I don't know if it's usually the case. Um, Today we'll do caching part 2 and wrap up caching and then follow through for the in-class exercise on caching. All right. Quick announcement. Based on the midterm, please go and review function pointer. And also how to use pointer. All right. There are quite a few samples that I saw that like that's not how to use pointer at all. Also, don't just throw a bunch of words in the box. I've seen a few of that. If you know what you're doing, I think most of the question I have will be pretty straightforward. If you don't, then a bunch of words in a box doesn't help because I don't know where is your answer. Well, the whole thing is your answer, but like, are you really getting at the thing? Assignment 4 is out. You might have realized that, especially you retaking this part, you might have realized that it's a lot of new material. The second part is all new. The first part is to be fun because now I give you a choice of which of the hard questions you want to tackle. So you might see that there's a lot of things you need to implement, but that's not the case. All right. Look at the total grade for that section with 70 points. Yes. You get extra credit if you do all. Yes. Feel free to do all of them, especially if you find it kind of fun to like look at this problem and see how you would fix and use and or XOR and all those things to do these tricks. All right. I I I cap it such that you only have to pick, I think, 3 hard questions. If you pick the rest, right? That should be kind of in line with previous semester. But if you want extra credit, there are way more hard questions for you to play around with. We now transition to the like when will A5 be okay? That's a great question. So the question is when is A5 is going to be released? So my plan is to do it next Tuesday, so that you have the basically 2.5 weeks on it. And I'll try to make the starter code a lot easier so that you don't have to like start from nothing. That you just need to make sure you implement the how to get the index, how to get the tag, and then some part of how to actually manage the cache. All right. So the quick recap on cache organization. Basically, the cache contains multiple cache blocks. Each block belongs to a set. All right. Each memory address is mapped to the certain part of the cache, which is a specific cache set. You will see in your in-class exercise today, which I do encourage everyone to work on it here so that you have questions, I can walk around and guide you through it. All right. Unless you go through this example on your own, it's going to be much harder to learn from what I do on the board from last week. When you do it on your own, you learn a lot. All right. But here's an example. Let's say I have an address. The address will go to only one of those sets. And when you go there, you just compare the tag to see if that's your data or not. All right. And the lookup, because the data in the cache is going to be just a significantly much smaller portion of what you have in DRAM because the cache is a lot smaller. So when you look it up, the data that you find might not be yours. You need the tag to see if that data is yours or not, right? So to look things up, you need 2 information. First is the index bit. The index bit are a part of your address that translate to the set number. So let's say the index bit is 110. 110 in binary is number 6 in decimal number. So you go to set number 6. And that's it. You have an address. The address tells you what set do you go to by using the index bit. Then the tag bit tells is that your data. If the tag match, that's your data. All right. And how to get the index bit? You can go through this example where in a block, it contains multiple bytes of data. So the last n significant bits are going to be reserved. For the exact bytes that you're trying to access, somehow I call this the byte in block bits. So it's basically log2 of the size of your cache block, and you're going to reserve the last n bits for this byte in block bits. Then, based on the cache specification, depending on the number of sets that you have, log2 of the number of sets is going to be the number of bits required for the index bits, which come next. Then the rest are the tag bits. So you extract the index bit from your address, then look at the tag bits. When you do the lookup, see if that's your cache or it's just someone else's cache block. And that's it. All right, it's as simple as that. There are steps behind it, but the whole thing is actually not too complicated if you follow these steps. And we talk about set associativity, which means that in a set, you can contain multiple cache blocks. A set associative cache is a cache design where there are multiple blocks per set. We will call this n-way cache, right? N-way cache, n-way set associative cache means that I have n blocks in a set. So if you go and read the CPU specification and say, hey, this is a 4-way set associative cache, it means that in a set, I have 4 blocks in there. All right. Set associative cache allows the case where it tries to give more room in the case that your data map to the same set a lot. It will give more room for more cache blocks to be in that set, right? But the downside is when you have to look it up, it's a little bit more complicated because now you have to compare multiple tags. You will end up with a lot more comparator in the hardware design. Now, again, with the set associative cache, we'll transition to the topic we need to talk about today, which is insertion and eviction. Imagine this room that has a lot of students, which I can't imagine. Anyway, so let's say that everyone is in this room, all the seats are taken. All right, let's imagine all the seats here are taken. A new student walk in the room. It basically means that I need to find an empty seat for the new student, right? Let's imagine this is a cache. My policy would dictate who do I kick out. It's as simple as that. I go to that set and select who to kick out. So that's the eviction policy. Insertion means that when the new guy comes in, right? Do I treat him? How do I treat him? Do I have more priority for the new block, or do I give them less priority for the new block? So now, with the direct map cache, by the way, direct map cache means that each set only have one block. Eviction is simple. Why? I go to the set, there's only one seat in them. Who do I kick? That guy, right? So eviction of the direct map cache is simple. You kick whatever is in there. Okay. For the set associative cache, you go to the set. You see, let's say it's a 4-way cache. You see 4 cache blocks. Now you have a choice. The issue involves 3 things. Insertion, how do I treat the new guy? Promotion, when I have access to the cache block, do I do anything with it? Eviction, if the set is full, who do I kick? All right. And the replacement, so the first thing we'll talk about is the replacement policy. When the cache is full, you need to find the block to kick, essentially. You need to find a block to kick. And it's a design choice. I can design a cache with a random policy. I look at this randomly and kick any block at random. I can do first in, first out. I can do least frequently used, I look at how frequent I access each of the block and I kick the block with the lowest number of accesses, right? Yes. Yeah, you got to the problem, right? Because the new guy will have how many access? One. So he's gonna get kicked next time, right? So that's the downside of the frequent access base. So if you are the CPU designer, which one are you gonna pick? Oldest use. So like the if I look at how what's the last time I used that block and pick the oldest, right? So what you just explained is this least recently used. And actually this is the default policy if you assume like most modern CPU, right? Why does that make sense? So you need to think about it this way, right? I want the policy that would maximize the chance of future access becoming a cache hit. So if I look at all the blocks, block A, B, C, and D, and it just turned out block C, for example, hasn't been used in 1,000 seconds, and the other three have been used in the last 1 millisecond. I better kick block C out, right? Because I haven't used for a long time, right? So that's the logical reason behind least recently used policy. Um, any question?
What's the difference between least recently used and not most?
Another great question. So let's say you have 4 blocks, right? And the last time I accessed this guy, oops, sorry, that finger. The last time I accessed that third block, and this is the LRU block, right? The least recently used policy would kick this guy, but the not most recently used policy would pick the other 3 blocks at random. And it turns out this one is more expensive to implement. This is cheaper to implement. So the reason why they are more expensive because I need to have some ordering for my all the blocks. It means that I have to keep track of where is the block that used the late like the last use for each of the block and compare them, right? But the fourth one, the not most recently used, is cheaper because if I access something, I just say that's the recent access. The rest are random. So it's much easier to implement. The actual policy used by modern CPU is like a mix of the two. It tries to imitate LRU or the least recently used, using the not most recently used. Like it's a multiple level of the not most recently used policy. Oh yeah. Least frequently used sounds like it makes sense as well, but the problem is then the new guy will have the frequency of access of 1 and he'll get kicked, right? First in, first out doesn't take care of when did I access this block, right? So it might not treat the recency of your access, if you will, like that well. And random can work in some scenario, but it's again this random policy, so it's not perfect. All right. So here's the least recently used. It's based on 2 things that we talked about last week: temporal and spatial locality. Temporal locality means that if I use some data, I'm likely to have to access that guy again. It's the nature of how you program. When you program, you reuse the variable a lot. So if you just use that variable, you are likely to use it again. Spatial locality is if you use that guy, you're likely to use the data that sits next to it. Why is that the case? Array access, for example, when you have a big array, you go through them this way. right? So it does exploit spatial locally because when you access the first item, you're gonna read the next item and so on and so forth as well, right? So the LRU policy exploit both of them. Benefit is this is likely to be effective. Downside, again, as I told you, you need to be able to kind of find the minimum number, right? Which doesn't sound too bad in software, right? If I ask you write a function that given an array, find the minimum. That's not too bad in software. So this thing is in hardware. So you don't have a lot of tools to implement in hardware. So it turns out that the complexity is not that we cannot implement it, but it's too complex. We better use the transistor for something else. I would rather have bigger cache, and I would use the imitation of the LRU, which is a lot cheaper to get the benefit of the LRU. All right. Any questions so far?
The last line there.
Oh, first in, first out queue. Basically, when you want to sort, right? One thing you can do is you can use the first in, first out queue where whenever you access something, you dequeue that guy and you enqueue them. So the guy in the front of the queue is going to be the oldest guy. The problem is then you have to have this FIFO queue in hardware to sort them, right? All right. Now, with the LRU policy, right, the next thing we can talk about is, let me ask this question. Let's say I have 4 cache sets. Like, not 4 cache sets, only one set, set 0. And then I have a 4-way cache. Can I engineer my program so that I have 0% hit rate? Huh? Right? How? Yeah, I just access 5 things in circle, right? That I just need to make sure those 5 things go to just 0. And those 5 things are not from the same block. It basically means that I'll evict each other all the time and you have no caches. We call this problem set thrashing. Set thrashing means that, well, let's say I use LRU, they all map to the same set. So let's say I have a 4-way cache, my code, my program go through A, B, C, D, E, and then back to A. Right? And let's say they just happen to map to the same set. Now, when I access A, B, C, D, and E, A, B, C, D is in a cache. When I access E, which one of this is a least the LRU block? When I'm trying to access E, which one is the oldest? A, right? So E will come in, kick A out. What's the next access? A. A just got kicked out. So A access go to DRAM. Who is the oldest guy here? B, right? So A would now kick B out, and then the next access is to B. So B comes in, kicks C out. Then the next access is to C. C comes in, kicks D out, right? So I can then engineer a program that would do this, right? This means that an LRU become effective, but even things like a random policy is better, right? E comes in, I pick things at random. There's a chance that it's not A, right? So a random policy in this case can be more effective, right? So let me give you this one example. How many cores are in your CPU? Let's say it's 4 cores, all right? I have a program that are running on the one of the CPU, and I say I want to build a program that is not fully attacking the first program, but I want to slow down the first program. can I make sure that I write a program to kind of flush whatever data program one that is running on the other CPU out of the cache? I can, right? I can write a for loop that builds the addresses in a way that would kick the other program's data out of my cache, right? So set thrashing can be quite important because you have to handle this. You basically you have to make sure that if there's a room in your cache, you use them. You can use them. It's not like everything is cluttered in one set, right? Any question about set thrashing before we go to insertion policy? Okay, so now the next thing is insertion, right? When a cache miss happens, I need to get the data from my DRAM. The DRAM will send the data back to the cache. The strategy is typically if you use the LRU policy, the new guy will be the most recently used because you just access them. All right. Any question? So this is simple. A new guy that comes in should be in the most recently used. Why do I bring this up? Why do I bring this up? Because there are also some cases where, how many of you, when you write a code, you initialize something in the beginning, like initialize array A to be 0? You do that quite a bit, right? If I do that, sometimes I will have a lot of cache miss because I do write once and that's it. I touch that location once and I'm gone, right? So there might be some design optimization that I can do to detect is my program doing that exact same thing? Because if I do that exact same thing, either put that in the LIU so I get kicked out right away, or just bypass the cache, don't put it in. All right. So another thing that we have to talk about now that we know about eviction is the promotion policy. Promotion means that if I access something already in the cache, update the access time so that you can do LIU. That's it. All right. When I access the cache block, promote them to the MIU position. This can be done by updating the bits that associate with the replacement policy. There are multiple types of cache misses. The first type is called compulsory miss. What does compulsory mean in English? What does the word mean? The word compulsory is like something that you must do, right? When you run a program and you never access this address before, and is that going to be in the cache? No, we call those guys compulsory miss. It's something that you have to do because you've seen this address for the first time. The only technique that, well, the technique that can fix this problem, sometimes we call this prefetching. This is where you try to predict future addresses that you need to use and put them in the cache ahead of time. The next type of cache miss is called conflict miss. Conflict miss is like, for example, the set thrashing problem. I have data going to the same set. Even though I still have the space in my cache, because they go to the same set, they kick each other out. So we call this the conflict miss. And as the name suggests, it's a conflict. They go to the same set and make the conflict. They kick each other out. The last type is called capacity miss, which is you basically run out of cache. The difference between a conflict miss and a capacity miss is a conflict miss will happen even though you have the room in the cache. Because they go to the same set, some set is empty, some set is full. Capacity miss is there's no room in the cache. It's filled up. That's why we call this the last type capacity miss. All right. Any questions so far? Yes.
Maybe that would do with conflict miss, right?
It can it be hard to deal with conflict miss?
How is it just find the next open spot?
So the thing is your address mapped to the set, right? So the way you deal with conflict miss typically is through better programming. So many of the program that you write in the future, somehow you call special library, right, to run certain parts of your program. And one optimization that you can do is to rewrite how you access your data so that you don't go to the same set at the same time, right? For example, and also you can also avoid capacity miss through programming as well. So let's say I have to do matrix multiply, right? Multiply A and B together, right? If I have a really large A and B, if my A and B is huge, right, they will fill in the cache for sure. So one of the common techniques that you can do is called block matrix multiply. You cut up A into smaller chunk and B into smaller chunk and do the multiply just for those two chunks. First, you make sure the chunk that you cut up is small enough that both of them fit in the cache. So when you do matrix multiply for the smaller chunk, everything is a cache hit, right? So again, programming, this is where programming comes into play a lot. And people who work in supercomputer, people who work in scientific computing, they would exploit the structure of the cache and rewrite your program in order to make sure that it's always a cache hit. It's one of the most important thing for them. Like make sure I write a program that is all a cache hit. If it's not a cache hit, I want to make sure that all my cache misses happen all at once to make use of the bandwidth. Instead of sending one miss at a time, I will send 100 misses altogether so that DRAM can process those in parallel. All right. So now when you look at caching, right? Now I have cache miss, cache hit, right? To measure the actual performance, right? You want to look at the cache hit rate or the cache miss rate. What are these? These are the ratio of the number of cache hits over the number of cache accesses. So let's say you want to access a cache 1,000 times, and 900 of your time of those accesses is a cache hit. It means that the cache hit rate is what? 90%, right? Then there's also the cost of the hit and the miss. Why is that the case? Again, a smaller cache is fast, a bigger cache are slower. So when you have a cache hit, even though the cache is a hit, the cache access is a hit, but it's to a bigger cache, it takes a lot more time to go there, right? Remember the 7-Eleven versus mall versus like your kitchen cabinet example. Then the total cost of the load, right? This is basically, if you look at all your data access on the aggregate time that you need to do to go access all this data, how much time does it take on average per memory access? For example, let's say I have the L1 and L2 that take L1 takes 2 cycles to finish, L2 takes 5. So it takes 2 cycles to access L1, take 5 cycles to access L2, take 25 cycles to access DRAM. All right. And you write a program that has 1,000 data access, 100 data access. 80% of them hit in L1, the other 80 that miss in L1 hit in L2. How many cycles does it take? So I'll go through this example, you do the next one, all right? Because every access has to go to L1, because that's my first destination, I check is my data there, right? Each access will spend 2 cycles, so that's 100 multiplied by 2, because I have to have all the access going to L1. Then how many has to go to L2? 20, right? So the other 20 has to go to L2, and how many actually miss in L2 and have to go to DRAM? 4, right? 25 multiplied by 4. Add them all up. So this is 200 plus 100 plus 100. So this is 400 cycles, right? So some quick thing. In reality, this is going to be lower because in reality, your CPU try to access a bunch of this together in parallel, right? But despite that fact, you can see that the time it takes to go to the cache matter, the number of cache hits matter. All right. Now this is 400 cycle. Let's go with the second example. The same specification for your DRAM, but let's say I look at the code and say, hey, maybe I can optimize it. I issue 10 more load, but now my hit rate is 95%. How many cycles does it take and is this better, right? So let's do a quick 5 minutes break in the middle. Let's do 10 minutes. In the meantime, please use the first or the last 5 minutes to go over this and answer me, is this better or is this worse? All right. For those of you who just came in, I have the exam right there. If you want to see your score with the feedback right there, just make sure you return it to me before the end of this class. All right. Yeah. So we will come back. For the folks online, we'll be back at 12:55. All right. All right. So how's the number? Is it better or worse? Better. Yeah. Yes, it could be better. Over here you have a way higher hit rate.
There's no DRAM.
That is, well, that can be like one DRAM or no DRAM. But if it's one DRAM, still 25 cycles is not bad, right? Most of the access in this case is in the L1. So you can imagine in real program where, so look at it this way, right? If your program runs for 1 second, right? And your CPU is clocked at what? Let's say 3.3 gigahertz. 1 second means that you can run about 10 to the like around three times 10 to the 9 billions of
time.
Yeah, a lot of instruction. I mean, that's why when you run any program, it's finished right away.
So 3 billion.
Yeah. So imagine if you have a cache hit on the accesses on your program, it does make a lot of effects, right?
So, let's say that you're playing like a video game.
Yeah.
No way you can play a video game with cache.
It's not, so two things, right? Does it use the cache a lot? Yes. Your code for the video game is designed so that when you have to, like say, when you have to compute those like particles, it try to fit those things in the cache. But on a GPU side, it also try to make sure it use all the GPU memory bandwidth so that you can issue the parallel execution of your memory accesses. Then on the calculation on the CPU side, it uses a lot of caching. Otherwise, your game, like, have you seen games where even though the graphic doesn't look that intense, but it's super slow? Yeah, that happens when you don't optimize your graphic engine. It can happen that way. Basically, it will consume more resources for the same task, right? That you have to render. And also that's also why like the graphic libraries can be quite important. Because if you implement those APIs really well and your programmer just call the APIs of like draw lines, draw dots, draw this texture, right? But internally implementation is cache friendly. From the get-go, it's fast, right? So these are a common techniques for.
How different is GPU tools?
So the way GPU works is different in a way that how it executes your program. So for the GPU, if you look at the single thread program, let's say you do one thing at a time, right? GPU is way slower, extremely slow compared to CPU. But what GPU has is the throughput. Instead of doing one thing at the same time, it do 1,000 things at once, right? So imagine the graphic workload, like I have to render one frame for your game, right? It basically, the first step is I draw dot, 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 dot. Then you connect the dot by drawing a line. A line is a linear equation. Y equals ax plus b, right? When you do the a multiplied by x, you don't draw one line. You just basically map 10,000 of lines at the same time, right? It's just a bunch of massive multiplication, the same operation, but it's done on a bunch of lines. That's why the GPU is really fast for this kind of workload that you can parallelize your program. But if you run a single thread program on a GPU, you will then realize that it's super slow. It's like way slower than a CPU. So one nice thing about the way our computer is built is CPU is really good at what they have to do. Like a normal general purpose computer that run everything like Microsoft Word and all those things. Then the GPU is taking care of parallel parts, like your workload, like video processing or rendering a frame in a game, or even when you process the animation, right? And we have to render the movie for your anime. GPU is really good for that. So another example is now, let's say I want to get the hit rate up, but now my program is changed, so I issue 1000 load. As you can see here, because I issue a lot more memory accesses, right? From the get-go, L1 access alone is 2000 cycles. So this is not an optimization, it actually runs slower, right? It actually runs slower because you have to issue way more number of loads. So to improve the performance of your program, you can rewrite your program to reduce the miss rate, to make sure your data access hit in the cache more often. One thing you can do is, for example, instead of looping over your entire data, do a smaller set of data at a time, so that when you compute the smaller set of data, it fits in the cache. You can also rewrite a program to reduce the number of memory accesses that you have to do. This can help quite a bit. Modern libraries actually that you use, like let's say you download a library like DirectX. Anyone heard of DirectX? Or like OpenGL? Those graphic libraries that many of your games rely on, right? They would be designed in order to squeeze out the performance of your graphic cards in that case, right? But the same libraries also apply for the CPU-based library. Many of them are designed to exploit your cache. So when you call this API, many of them are actually being optimized to give better performance. One thing they would do is they would actually check the size of your cache internally in the library. There's a command in Linux you can type in. I will print out the size of L1, L2, and everything. Then you, based on the configuration, right? You can then re-optimize things in the library, like how big is the data you're gonna put in, so that it fits in the cache for each CPU you're running on. My last word of advice is cache hit. Even though these are something that is controlled by the hardware, cache hit actually matter because it make the performance jump up quite a lot. Like level 1 cache is 3 cycles, level 2 cache is 10. DRAM is like 25 or more, right? That's a lot of time that you waste if you don't hit the cache, so that matters for performance. Now, before we go to the in-class exercise, the last thing I need to talk about is how do I handle the write? Why is that important? So let's say I have a CPU, right? And I have L1 right here, L2 right here, and then here's my DRAM. And let's say the CPU accesses the address in DRAM that has the value 2 right now. That address has the number 2 in them, all right? When I access this, I bring them over to both the L1 and the L2, right? So this address will be in the block. In the block, there's a value number 2. What would happen if I update the value from 2 to 3? You see a problem here? First of all, the address will hit in L1, right? Because I have that block in L1. I go and update L1, say, hey, number 2, gone. Number 3 is a new value. When the cache block is written to, the data actually change. So you need to make sure you propagate the change to DRAM. Why is that the case? That's the real location of your data, right? You need to make sure at some point DRAM has the updated value. So what can we do? One thing we can do is what we call write through. Write through basically means this. When I change this to 3, I would change everything to 3. I would write this whole thing through all my hierarchy to make sure DRAM has 3, L2 has 3. All right. Any questions so far? So that's a write-through policy. All right. It's simple. It ensures that everything is up to date. Now let me ask you this one question. Let's say my CPU read the address, and then I write number 3, which is what you saw earlier, right? Then I write number 4, then I write number 5. So I write number 4 to this, then I write number 5 to this, then I write number 6, and I don't read from it until this point, right? Do I have to update DRAM from 3 to 4 to 5 to 6? Or can I wait? I mean, technically, if I access the address, I will hit in the L1, right? So what's the value that I see? 6, right? So even though in DRAM, it's still the old value, it can be still the number 2 in DRAM. I hit the L1, right? Now, my question is, eventually I have to update DRAM to 6. The question is when? Yeah, you almost get the point. Whenever that number 6 gets kicked out from the L1, if it's not in the L1, but it's in L2, and I didn't update L2 yet at the point, what's the number I'm reading? In this case, I'm reading 3, right? Which is a wrong value. So the next policy, we call this write back. Write back means that whenever I kick something out of the lower level cache, I would need to make sure if there's anything that I have to update, I update the upper level cache. So in this case, if I need to kick this block out, I will update this to 6, and it will keep remaining in the L2. I don't have to update DRAM until this guy gets kicked out of L2. Then I just update DRAM to 6. The benefit here is you don't have to do a frequent update. You only update as needed, right? Only when you have to absolutely update the upper level cache, then you update. Most modern design would use a write back because it saves the bandwidth. You don't have to write to DRAM many times. You don't even have to go there. When you update, just update the cache level that's close to you. That's all. All right. Any questions so far? Now that's it for today's lecture. I really want you to transition to the in-class exercise for both the assembly and the caching questions. Based on the midterm, I feel like you gotta at least try this. Okay, before the final. All right, so I want to dedicate more time for this. Virtual memory will start on Thursday. Now you see the in-class exercise, go to the caching question. I believe there are 2 of them. I'll walk around to answer any question, including your midterm grading. If you have any question on your midterm, let me know. All right. That's it for today's lecture. Please transition to in-class. Yes, for those online, if you want to come over and look at your midterm, yes, you can. Once, basically, I will update Canvas with your score tonight or tomorrow morning. Basically, by tomorrow 9 a.m., you'll see your score on Canvas. As I told you, I curved it so that everything is out of 75. If you score more, you get the extra credit. Yeah, people who get like 20% extra credit. All right, so, well, again, please transition to in-class.